Hello, let's dive into something that might just change the way you think about regression models forever. We're talking about lasso regression, but before you roll your eyes thinking this is just another dry statistical concept, hear me out. Imagine you're an artist sculpting a masterpiece. You start with a big rough block of marble, but instead of adding material, you're chipping away the unnecessary parts until only the most essential, beautiful features remain. That's exactly what lasso regression does to data. It refines, sharpens, and eliminates the noise to reveal the core elements that truly matter. Now, we have a lot to explore. We'll start with why ordinary least squares, OLS regression, the classic go-to method, isn't always the hero we think it is. Sensitivity to outliers, trouble handling multicollinearity, and an inability to navigate complex datasets, these are all cracks in its foundation, and that's where Lasso steps in, like an expert sculptor, applying just the right amount of pressure to carve out a model that is simpler, stronger, and more interpretable. We'll talk about regularization, this magic ingredient that prevents overfitting and tames messy data. We'll break down L1 regularization, the heart of Lasso, and see how it shrinks coefficients, filters out redundant variables, and leaves us with a cleaner, more reliable model. But here's the twist. This method isn't just about making models look nice and simple. It has deep practical applications. Think finance, where it picks the most critical factors for credit scoring. Think healthcare, where it selects the key genetic markers in medical research. Think marketing, where it identifies the real drivers behind consumer behavior. We'll compare it to Ridge Regression and explore where each shines. We'll look at how the tuning parameter, Lambda, is the real game changer. It's like the volume knob that controls how aggressively we trim down unnecessary predictors. And of course, we'll see its limitations too, because nothing is perfect, right? So here's my question for you. What happens when we start applying these techniques to real-world data? Can we really simplify without sacrificing accuracy? Is there a catch? Let's find out. Slide 1. Here we go. Okay, let's kick this off with a question. Have you ever felt like your predictive models are bloated, noisy, and just full of variables that don't seem to add much value? Like a suitcase packed with things you might need but never actually use? Well, today we're going to learn how to declutter those models, keeping only what truly matters. Welcome to Lasso Regression, your personal Marie Kondo for data science. If a variable doesn't spark joy, or more importantly, statistical significance, we toss it. But hold on, this isn't just about making models look pretty. We're about to explore a game-changing technique that sharpens predictive power, reduces complexity, and makes machine learning models far more efficient. Now, before we dive in, let's address the big elephant in the room: ordinary least squares, OLS regression. If you've ever taken a stats class, you've probably encountered it. It's the gold standard, the classic workhorse of regression models. OLS is great at fitting lines to data, making predictions, and explaining relationships between variables. But here's the problem. It assumes the world is nice, clean, and well-behaved. Spoiler alert, it's not. OLS is like that friend who trusts everything they hear. It gives equal importance to every predictor in the model, even the ones that are just noise. Got outliers? OLS freaks out. Too many correlated variables? OLS doesn't know which one to trust. And if you're working with high-dimensional data, think thousands of predictors, OLS turns into a mess, overfitting like crazy and making your predictions about as reliable as a weather forecast a month in advance. And this is where Lasso Regression steps in, like a data-driven superhero. What if I told you there's a way to not just build a regression model, but automatically select the most important variables, a way to reduce complexity, eliminate redundancy, and create a model that's lean, efficient, and more accurate? Lasso doesn't just estimate coefficients like OLS, it shrinks them. It applies a penalty to force some coefficients towards zero, effectively removing weak predictors from the model entirely. That means we're not just predicting, we're curating the best set of variables, turning a cluttered mess into a sleek, optimized machine. Now, here's the fun part. How does it actually work? How does Lasso determine which variables to keep and which to throw away? And what's the deal with this magical penalty term called L1 regularization? Stick around, because in the next slide, we're going to break it down and uncover why this technique is a must-have in your data science toolbox. Get ready, we're just getting started. All right, now that we've set the stage, let's talk about the method that Lasso Regression is trying to fix, the good old ordinary least squares OLS regression. If regression models were cars, OLS would be the classic sedan, reliable, widely used, but struggling when the road gets rough. So what exactly is OLS? Think of it as a way to draw the best fitting line through your data points. The idea is simple. OLS finds a line that minimizes the sum of squared errors, SSE, basically the difference between what your model predicts and the actual values. It's like trying to get the most accurate dart throws on a board, reducing how far off each dart lands from the bullseye. But here's where things get interesting. OLS comes with a set of assumptions that, in an ideal world, make everything work smoothly. Let's quickly walk through them. Linearity. The relationship between the independent variables and the dependent variable should be straight-line-ish. If your data behaves like a roller coaster, OLS is going to struggle. Independence. Each observation should be independent of the others. If you're dealing with time series data or anything that has patterns, OLS might misfire. Homoscedasticity. The variance of the errors should remain constant across all levels of the independent variables. In simpler terms, OLS assumes errors are evenly spread out, not increasing or decreasing unpredictably. Normality. The errors, or residuals, should be normally distributed, which makes inference easier and more reliable. Now, these assumptions sound great in theory, but in the real world, they break all the time. And when they do, OLS starts showing its weaknesses. First, OLS is highly sensitive to outliers. Imagine you're trying to calculate the average salary in a company, and Jeff Bezos is somehow on the payroll. That one extreme value can totally skew your results, making OLS go haywire. Second, OLS struggles with multicollinearity. This is when two or more independent variables are highly correlated. It's like having two friends who always tell you the same story. Your model doesn't know which one to listen to. This inflates the variance of the coefficients, making them unstable and unpredictable. And finally, OLS doesn't handle complexity well. If you're dealing with high-dimensional data, where you have hundreds or thousands of predictors, OLS will happily fit them all, but it won't tell you which ones actually matter. It just overloads itself with noise, leading to overfitting. So, while OLS is a solid foundation, it's clear that we need something better when the data gets messy. We need a method that controls complexity, eliminates unnecessary variables, and keeps only what's important. Enter Lasso Regression, a model that doesn't just estimate coefficients, but actually shrinks them, filtering out the ones that don't contribute much to the prediction. And here's the million-dollar question. How does Lasso do this? What's this magical penalty term that helps it clean up our model? That's exactly what we're uncovering next. Stay with me. This is where the real magic begins. All right. Now that we've seen the cracks in ordinary least squares, OLS regression, it's time to talk about the solution, regularization. This is where we start turning a chaotic, overcomplicated model into something lean, powerful, and actually useful in real-world scenarios. But before we jump straight into Lasso, let's first understand why we need regularization in the first place. Think of it like this. Imagine you're preparing for an exam. You have a massive textbook with every possible detail you might need, but you only have a few hours to study, do you? Try to memorize the entire book word for word. Focus only on the key concepts that are most likely to be tested. If you pick option 1, you're doing what OLS does. It memorizes everything, including the irrelevant details, which is great for the training data, but terrible when new questions, new data come up. This is called overfitting, and it's one of the biggest problems in regression modeling. Overfitting is when your model is too good at capturing patterns from the training data, including noise and random fluctuations that don't actually matter. It makes your model look perfect on paper but perform horribly on new, unseen data. We don't want that. Then there's multicollinearity. OLS doesn't know what to do when multiple variables are highly correlated. Imagine you're in a noisy room with two people telling you the same story at the same time. OLS tries to listen to both equally, but that just leads to confusion. Regularization helps by making the model pick just one of them, making everything clearer. And finally, we need to talk about parameter shrinkage. A good model isn't just about having the right variables. It's about making sure they have the right influence. Some predictors should have a big impact, others should have almost none. But OLS treats them all with the same level of importance, which can lead to poor generalization. Regularization, on the other hand, shrinks the less important coefficients, reducing their impact or even eliminating them completely. So what's the solution? Regularization. This is where we introduce an extra term in the regression equation, a penalty that stops the model from going overboard. It forces the model to focus only on the most important variables, creating a balance between complexity and simplicity. And guess what? There's more than one way to do this. There's L2 regularization, which leads to Ridge regression, and L1 regularization, which gives us Lasso regression. But here's where things get interesting. Lasso doesn't just shrink coefficients. It does something even more powerful. It eliminates them entirely. It forces some predictors to exactly zero, meaning they get completely removed from the model. And that's why Lasso is a game changer. It's not just improving accuracy, it's automatically choosing the most important features for you. But how does Lasso actually achieve this? How does it decide which variables stay and which ones get the axe? That's what we're tackling next, as we break down L1 regularization and why it's the secret sauce behind Lasso's success. You don't want to miss this. All right, let's talk about what's really happening under the hood with Lasso regression, but in a way that actually makes sense. No cold mechanical formulas, just a natural way of thinking about it. So imagine you're trying to build the perfect team, but you're working with a budget. You can't just keep adding expensive players forever. You have to make tough choices about who actually contributes and who's just taking up space. That's exactly what Lasso does to your regression model. It forces the model to make decisions about which predictors really matter and which ones can be cut. It starts just like regular regression. The whole point of regression is to find a line that best predicts the outcome by minimizing how far off the predictions are from reality. The way this works is by looking at each prediction, comparing it to the real value, and measuring how big the difference is. These differences are called errors, and the goal is to make those as small as possible. In ordinary regression, the model tries to find the best fitting line by adding up all those errors, squaring them so that negative and positive errors don't cancel each other out, and then trying to make that total as small as possible. That's the basic rule. Keep the errors as low as you can. But here's where things go wrong. If you have a ton of different predictors in your model, it's going to try to fit all of them, even the ones that don't actually help. It doesn't care about simplicity, it just cares about making the errors small, and that's where overfitting happens. Overfitting is like memorizing an entire textbook instead of studying just the key points. Sure, you know every detail, but when it comes to answering new questions, you get confused because you focused on everything instead of what really mattered. That's exactly what happens when a model gets too complex. It starts picking up random noise instead of real patterns. Now, this is where Lasso steps in. Instead of just focusing on reducing errors, it adds a second rule. It says, yes, we want to make good predictions, but we also want to keep the model simple. It does this by adding a penalty, a sort of built-in punishment for making things too complicated. And this penalty gets stronger the more variables the model tries to use. The cool part, if a variable isn't really contributing much, this penalty starts pushing its influence down until, at some point, it gets removed entirely. It's like having a coach that says, look, if you're not pulling your weight on the team, you're out. And that's the magic of Lasso. It doesn't just reduce the importance of weak predictors, it completely eliminates them, leaving you with only the most valuable ones. And there's a dial that controls how aggressive Lasso is with this penalty. It's called Lambda, and it works like a filter. If Lambda is set to 0, then Lasso doesn't do anything, and we're back to regular regression. If Lambda is cranked up too high, it starts cutting everything, leaving only the absolute strongest predictors. The trick is to find the sweet spot, where we get rid of the useless stuff while keeping the important details. And that's the big difference between Lasso and Ridge Regression, which is another type of regularization. Ridge doesn't cut anyone from the team. It just reduces their importance a little bit. Lasso, on the other hand, isn't afraid to make the tough calls. It forces decisions, which makes it perfect for situations where you have way too many predictors and you need a model that focuses on what actually matters. So, now that we know how Lasso picks and chooses its variables, the next big question is, how do we actually find the perfect value of Lambda? How do we make sure we're filtering out just the right amount without going too far? That's what we're diving into next. This is where things get really practical. Now we're getting into the core mechanic that makes Lasso regression work. The penalty term. This is where Lasso moves beyond ordinary regression and starts making real intelligent decisions about which variables to keep and which ones to throw away. So let's go back to our idea of building the perfect team. Imagine you have a bunch of players, each with a different level of skill. Some are all-stars, some are just average, and some are just taking up space. In a normal regression model, you'd include everyone, no matter how little they contribute. But Lasso adds a budget constraint, a rule that forces you to be selective. You don't get to keep everyone. You have to prioritize. That's what the penalty term does. It controls how much freedom the model has when assigning importance to different variables. If a predictor is strong and genuinely valuable, it stays. But if it's weak, if it barely contributes, Lasso starts shrinking it down. And if it's really not pulling its weight, it gets cut entirely. Its coefficient reduced all the way to 0. Let's break down what's happening behind the scenes. When we fit a Lasso model, we're not just trying to minimize error, we're also minimizing complexity. The penalty term is what makes that happen. It's like a built-in referee that watches every variable and asks, are you really needed here? If the answer is no, the variable is pushed out of the equation, and the intensity of this penalty is controlled by Lambda. Think of Lambda like a knob that adjusts how aggressive Lasso is. If Lambda is set to 0, the penalty disappears completely. The model behaves just like ordinary regression, keeping everything, even the useless variables. If Lambda is turned up just a little, the weak predictors start getting smaller and smaller. They're still there, but they don't have much influence. If Lambda is pushed even higher, the weaker predictors start vanishing completely. Their coefficients drop straight to 0, meaning they are eliminated from the model entirely. This is what makes Lasso so powerful. Unlike other models that just tweak the importance of predictors, Lasso actually removes the ones that aren't contributing much. That means it's doing two things at once. improving prediction accuracy and simplifying the model. And here's where things get really interesting. The right choice of lambda depends on the data. If lambda is too low, you keep too many variables and your model stays cluttered. If lambda is too high, you might start losing important predictors that actually help with accuracy. So how do we find the perfect balance? That's what we're diving into next. The impact of lambda on model performance and how we tune it just right. Stay with me because this is where we start applying everything we've learned. So now that we understand the role of lambda in lasso regression, let's talk about how it actually shapes the final model, how it impacts the coefficients, how we optimize it, and how we make sure we're striking the perfect balance between accuracy and simplicity. We've already seen that lasso doesn't just estimate coefficients like ordinary regression, it shrinks them. The amount of shrinkage depends on lambda, and this is what controls whether a predictor stays in the model, gets reduced in influence, or disappears altogether. But what does that actually look like? Imagine we have a data set with multiple predictors. Some are very strong and clearly important, others have a small influence, and some are just noise. If we don't apply any penalty at all, the model keeps everything, assigning a coefficient to every variable, even the weak ones. This is what happens when lambda is set to 0. Now, as we gradually increase lambda, something interesting happens. The weak predictors start losing weight. Their coefficients get smaller and smaller. If a predictor isn't contributing much to the model's predictive power, it gets squeezed down. And if we keep increasing lambda, at some point, many of those coefficients shrink all the way to 0. That means those variables are being completely removed from the model. The higher the lambda, the more aggressive this selection process becomes. This is what makes Lasso so powerful. It's not just reducing the influence of weak predictors, it's actively eliminating them, making the model simpler, faster, and easier to interpret. It's like a sculptor carving away unnecessary pieces of stone, leaving behind only the essential shape. But here's the catch. If we push lambda too high, we don't just remove weak predictors, we start shrinking even the important ones. The model becomes too simple, and it starts losing valuable information. That's where we run into underfitting, the opposite problem of overfitting. The model is now too restricted and can't capture enough of the real patterns in the data. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. So the goal is to find the right lambda, one that keeps the model lean, but doesn't strip away critical information. How do we do that? We don't just guess. We optimize it through a process called cross-validation. Here's how cross-validation works. First, we split our data set into multiple parts, some for training, some for testing. Instead of using all our data at once, we train the model on one portion and test it on another. Then, we repeat this process with different values of lambda and see how well the model performs. The idea is simple. If the model performs well on training data but fails on test data, that's a sign of overfitting. If it does poorly on both, that's underfitting. We're looking for the lambda that gives us the best balance, keeping the model accurate without making it unnecessarily complex. And this process isn't just theoretical. It's the gold standard for tuning machine learning models in the real world. Whether you're working in finance, healthcare, or marketing, getting lambda right can make or break your model's ability to predict accurately. But there's still one big question left. What happens when two variables are telling almost the same story? What if two predictors are highly correlated? Does Lasso keep both, or does it choose one? That's what we're exploring next. The way Lasso handles correlated variables is what makes it truly unique, and it's the reason why it's often preferred over traditional regression. Stick around. This is where things get really interesting. All right, now we're stepping into one of the most fascinating aspects of Lasso regression, how it deals with correlated variables. This is where Lasso goes beyond just shrinking coefficients and actually starts making decisions about which variables get to stay in the model and which ones are cut. Imagine you're running an election campaign and you've got two advisors giving you almost identical advice. They're saying the same things, making the same predictions, and contributing nearly the same insights. Now you don't need both. Keeping both would just be redundant. What do? You pick one and move forward. That's exactly what Lasso does when it encounters correlated predictors. Let's take a step back and understand why this even matters. In ordinary regression, when two variables are highly correlated, it creates a problem called multicollinearity. This makes the model unstable because it doesn't know which variable to trust more. Imagine trying to listen to two people speaking at the same time. It's confusing and it makes it hard to figure out which one is really contributing new information. With traditional regression methods like OLS, this leads to inflated coefficients, meaning the importance of those variables gets exaggerated. The model struggles because it tries to balance both variables, and that creates uncertainty in the predictions. This is bad because we want our models to be clear, stable, and interpretable. Now, here's where Lasso comes in and handles things differently. Instead of letting both correlated predictors fight for space in the model, Lasso simply chooses one and eliminates the other. The way it does this is by applying the L1 penalty, which forces some coefficients all the way down to 0. If two predictors are providing almost the same information, Lasso won't keep both. It will shrink one of them to 0, effectively removing it from the equation. Let's visualize how this plays out. Imagine we have two predictors. One is the size of a house in square feet. The other is the number of rooms in the house. These two are highly correlated because bigger houses tend to have more rooms. If we feed both into an ordinary regression model, it will try to assign importance to both, making the model unstable. But Lasso will recognize that these two variables are essentially saying the same thing. Instead of keeping both, it will pick one, either house size or number of rooms, and completely drop the other. This is one of the biggest advantages of Lasso, unlike Ridge Regression, which simply shrinks coefficients without removing them. Lasso actually performs feature selection automatically. That means it doesn't just reduce redundancy, it actively simplifies the model, making it more interpretable and reducing the risk of overfitting. But here's an interesting twist. Lasso doesn't always choose the right variable. Since it just picks one from a group of correlated predictors, it doesn't necessarily keep the one that has the most logical meaning. Sometimes the variable that survives is just the one that happened to have a slightly stronger initial correlation with the outcome. That means we still need to be careful when interpreting the results and understanding why certain variables were kept while others were removed. So now that we know how Lasso handles correlated features, the next big question is, how does it affect the overall model structure? How does it change the way we think about building and interpreting regression models? That's what we're tackling next as we explore the tuning parameter Lambda and its effect on model coefficients. This is where the final shape of our model is determined, so stick with me, it's all coming together now. Now we're diving into one of the most important elements of Lasso regression, Lambda, the tuning parameter. This is the key factor that controls everything we've talked about so far. It determines how much we shrink the coefficients, how many variables get removed, and ultimately how simple or complex our final model will be. If Lasso is the sculptor cutting away unnecessary details, Lambda is the chisel. It decides how deep the cuts go. So what exactly is Lambda? Think of it as a control knob for regularization. It's the setting that tells the model how aggressive it should be in penalizing large coefficients. The higher the Lambda, the stronger the penalty, and the more variables get pushed out of the model. The lower the Lambda, the weaker the penalty, meaning we keep more variables and get closer to ordinary regression. Now, let's see what actually happens as we adjust Lambda. If lambda is set to 0, we completely remove the penalty. That means Lasso behaves just like traditional OLS regression. It keeps all the variables, regardless of whether they are useful or not. There's no shrinkage, no feature selection, and if we have too many predictors, we're likely to overfit. This is like refusing to edit a long-winded essay. It may contain good information, but there's also a lot of unnecessary fluff. If lambda is very small but not 0, we start to see slight shrinkage. Some of the weaker coefficients start getting smaller, but everything is still included in the model. At this stage, we're reducing overfitting just a little, but we're not eliminating any variables yet. As we increase lambda, we begin to see the real power of Lasso. The weakest predictors start shrinking faster and faster, and eventually, some of them drop all the way to 0. These variables are now completely removed from the model, meaning we're automatically performing feature selection. We're keeping only the most relevant predictors while discarding the rest. This is the sweet spot where Lasso really shines. It makes the model simpler, more interpretable, and better suited for new unseen data. But if lambda is too large, we start running into a new problem, underfitting. Now, even the important variables are being shrunk too much, and the model loses its predictive power. Imagine summarizing a book in just one sentence. You've simplified it so much that you've lost all the important details. A model that underfits doesn't capture enough of the real patterns in the data, making it just as bad as an overfitted one. So, how do we find the perfect value of lambda? This is where things get practical. Instead of just guessing, we use a method called cross-validation. Here's how it works. We take our dataset and split it into multiple parts, some for training, some for testing. Then we train the model using different values of lambda and see how well it performs on test data. The lambda that gives us the best balance between accuracy and simplicity is the one we choose. This is how we make sure our model isn't too complex, but also isn't too simple. It's just right. This process is absolutely critical in real-world applications, whether we're working with financial models, medical predictions, or marketing data. Tuning lambda correctly can mean the difference between a model that makes great predictions and one that completely misses the mark. Now, we know that lambda controls how many variables stay in our model and how much we shrink the coefficients. But there's still one last question left. How do we evaluate the final model once we've selected lambda? How do we know if we've made the right choices? That's exactly what we're covering next as we step into final model evaluation and feature selection in Lasso Regression. This is where everything comes together. So stay with me, we're almost at the finish line. Okay, we've now fine-tuned our model by selecting the right lambda, but before we celebrate, there's one last critical step, evaluating the final model. This is where we make sure we've actually built something useful. Did Lasso make the right choices? Did we keep the right variables and eliminate the ones that weren't helping? And most importantly, is our model performing well on real data? Lasso regression isn't just about making predictions, it's about making smart predictions using only the most relevant features. That means after we've applied our penalty, we need to carefully inspect which variables were kept and which ones were removed. This process is known as feature selection, and it's one of the most powerful aspects of Lasso. Let's go back to our earlier idea of Lasso as a sculptor. After carving away the unnecessary parts, we're left with the final shape. But before we put it on display, we need to take a step back and analyze what's left. The variables that survived the Lasso penalty are the ones that the model considers most useful. They're the strongest predictors of the outcome. These are the features that really matter. Now, how do we know if we've chosen the right features? This is where model evaluation comes in. We need to check whether the final model generalizes well to new data. Here's how we do it. First, we test the model on data it hasn't seen before. This is called out-of-sample validation. If the model performs well on training data, but fails miserably on test data, that means we've overfitted and need to adjust lambda. If it performs well on both, we've found the right balance. Second, we check the error metrics. One of the most common ways to measure a regression model's accuracy is by looking at the mean squared error, MSE. This tells us how far off, on average, our predictions are from the actual values. A lower MSE means our model is doing a great job. Third, we look at the coefficient values themselves. If Lasso has eliminated too many variables, we might see that the model is underfitting, meaning it's too simple and missing important patterns. If it has kept too many, we might still be dealing with unnecessary complexity. The key is to inspect which variables survived and ensure they make sense in the context of our problem. But here's something really important. Lasso doesn't always get it right on its own. Because it aggressively removes variables, sometimes it might drop predictors that are actually useful, but just happen to be weaker in the dataset. This is why feature selection isn't just a mathematical process. It also requires human judgment. A domain expert might look at the final model and say, wait a second, this variable is important in real life, even if Lasso dropped it. That's when we might need to adjust Lambda slightly or bring back certain features manually. Now let's step back and ask the big question, why does this all matter? In real-world applications, feature selection is the difference between a model that just fits the data and a model that gives deep, meaningful insights. A financial analyst doesn't just want to predict stock prices, they want to know which factors truly drive those prices. A medical researcher doesn't just want to classify diseases, they want to know which genetic markers are most important for early detection. That's what Lasso gives us. So now that we've selected the best predictors and confirmed our model is performing well, the final piece of the puzzle is understanding how Lasso actually solves the problem of multicollinearity. We've already seen how it picks between correlated variables, but now let's dig deeper into why this is such a game changer for high-dimensional data. This is where Lasso proves itself as one of the best tools for modern data science. Let's keep going. We're almost there. All right, now we're at one of the most important benefits of Lasso regression, handling multicollinearity. We touched on this earlier when we talked about how Lasso picks between correlated predictors, but now let's dig deeper into why this is such a game changer, especially for high-dimensional data. Multicollinearity is one of those sneaky problems that can ruin a regression model without you even realizing it. Imagine you have multiple predictors that are all saying the same thing in slightly different ways. Maybe you're predicting house prices and you have three variables: square footage, number of rooms, and number of bathrooms. These are all related. Bigger houses tend to have more rooms and more bathrooms, so they're collinear. In a normal regression model like OLS, this creates a big problem. The model doesn't know which variable to trust. It tries to spread the importance across all of them, but this inflates the coefficients and makes the whole thing unstable. It's like trying to balance on a wobbly chair, one small change in the data, and suddenly the coefficients shift dramatically. That makes your model unreliable. This is where Lasso steps in and forces a decision. Instead of struggling with multiple correlated predictors, it simply picks one and shrinks the others to zero. In our house price example, Lasso might decide that square footage is the best predictor and completely remove number of rooms and number of bathrooms. The result? A model that's more stable, more interpretable, and less likely to overfit. Now, here's something interesting. Lasso doesn't always pick the most logical variable. If two variables are highly correlated, it doesn't necessarily keep the one we'd expect. It just keeps whichever one happened to have a slightly stronger initial correlation with the outcome. This is why, in some cases, we still need to manually inspect the final model and make sure it makes sense. But overall, this ability to handle multicollinearity is one of the biggest reasons Lasso is so widely used. In fields like finance, genetics, and marketing, where you might have hundreds or even thousands of variables. Multicollinearity is everywhere. Traditional regression models break down under that kind of complexity, but Lasso thrives in these environments. It simplifies the model, removes redundancy, and makes sure we're only keeping the variables that truly matter. And that leads us to our next big topic: the advantages of lasso regression overall. We've seen how it selects features, how it prevents overfitting, and how it handles correlated variables, but now let's zoom out and look at the big picture. Why should we use lasso instead of other regression methods? What are its biggest strengths, and where should we be cautious? That's what we're tackling next, so let's keep going. Now that we've seen how lasso regression handles feature selection, prevents overfitting, and deals with multicollinearity, let's zoom out and look at the big picture. The major advantages of using lasso regression and why it's such a powerful tool in machine learning and data analysis. One of the biggest strengths of lasso is its ability to automatically perform feature selection. In traditional regression, you have to manually decide which variables to keep and which ones to remove. That's time-consuming, and it often leads to human bias. But Lasso does this for you. By shrinking the coefficients of weak predictors down to zero, it removes unnecessary variables from the model, leaving only the most important ones. This makes Lasso an ideal choice for high-dimensional datasets where you might have hundreds or thousands of predictors, and you need a method to filter out the noise. Another major advantage is that Lasso reduces model complexity, which helps prevent overfitting. Overfitting happens when a model learns the noise in the training data instead of the actual patterns. It might perform perfectly on the training set, but as soon as it's tested on new data, the accuracy drops because it memorized irrelevant details instead of learning the true relationships. Lasso counteracts this by applying a penalty that discourages large coefficients. This forces the model to focus on only the most essential predictors, leading to better generalization and improved accuracy on unseen data. Then there's multicollinearity, which we just covered. Unlike ordinary least squares regression, which struggles when predictors are highly correlated, Lasso naturally eliminates redundant variables, making the model more stable and interpretable. This is particularly useful in fields like finance, genetics, and marketing, where many predictors are interconnected, and you need a way to identify which ones truly matter. But one of the most practical benefits of Lasso is that it makes models easier to interpret. In many real-world applications, we don't just want a model that makes accurate predictions. We want to understand why those predictions are being made. By reducing the number of predictors, Lasso gives us a clearer picture of the most influential factors in our model. This is crucial in fields like healthcare, where researchers need to pinpoint which risk factors contribute to a disease, or in business, where executives need to know which marketing strategies drive revenue. And let's not forget about computational efficiency. In large data sets, running traditional regression models can be slow and resource intensive. But because Lasso reduces the number of predictors, it speeds up computation and makes model training more efficient. That being said, Lasso isn't perfect. While it's great at feature selection, it sometimes makes arbitrary choices when dealing with correlated variables. Instead of distributing importance across multiple related predictors, it picks one and discards the rest, even if some of the discarded variables contain useful information. And because it forces coefficients to exactly zero, it can introduce bias in cases where all predictors have some importance, just at different levels. So when should we use Lasso? It's perfect when we have a lot of predictors and we need to simplify our model while keeping only the most important features. It's great when we're dealing with overfitting, and it's a go-to choice when we want an interpretable model. But if we have highly correlated variables that all carry meaningful information, or if we believe that every predictor should contribute in some way, we might want to explore other regularization techniques like ridge regression, which we'll compare next. Now that we've seen Lasso's strengths, the next question is, how does it stack up against ridge regression? Both methods use regularization to improve predictions, but they do it in different ways. One shrinks coefficients to zero, the other spreads out the penalty more evenly. But which one should we use and when? That's what we're tackling next, so stay with me. Now that we've seen the strengths and trade-offs of Lasso regression, let's compare it to another powerful regularization technique, Ridge regression. Both Lasso and Ridge use regularization to improve model performance, but they do it in fundamentally different ways. Choosing between them can have a huge impact on the quality of your predictions. Let's start with what they have in common. Both methods introduce a penalty term to prevent overfitting. Instead of letting the model assign any values it wants to the coefficients, they apply a constraint that forces the model to keep things under control. This helps generalize the model so it performs well not just on training data but also on unseen data. Now here's where things get interesting. How they apply the penalty is completely different. Lasso uses L1 regularization, which applies a penalty on the absolute values of the coefficients. The effect, it forces some coefficients all the way down to zero, effectively removing certain predictors from the model entirely. That means Lasso doesn't just shrink coefficients, it performs feature selection, keeping only the most important variables and eliminating the rest. This makes Lasso incredibly useful when we have a high-dimensional dataset with a lot of predictors, but we need to identify which ones truly matter. Ridge, on the other hand, uses L2 regularization, which applies a penalty on the squared values of the coefficients. This means Ridge shrinks all coefficients but never sets any of them to zero. Instead of eliminating variables completely, it keeps all predictors in the model but reduces their impact. Ridge is great when we know that all predictors carry some level of importance, and we just need to stabilize the model by preventing any one variable from dominating. Here's a simple way to think about it. Imagine you're packing for a trip. If you're using Lasso, you're deciding which items are essential and leaving the rest at home. You only bring what's absolutely necessary. If you're using Ridge, you bring everything, but you pack lightly, making sure no single item takes up too much space. Now, when should you use Lasso? It's best when we have too many variables and we suspect that some of them aren't useful. If we want automatic feature selection and a simpler model, Lasso is the way to go. It's especially helpful when dealing with datasets that have more predictors than observations, or when we suspect that many variables are irrelevant. And when should you use Ridge? It's the better choice when we believe all predictors carry some weight, but we want to control how much influence each one has. If we have multicollinearity, where multiple predictors are highly correlated, Ridge helps stabilize the model by distributing the penalty more evenly. It's also useful when we're working with small datasets where we can't afford to drop variables entirely. But what if we want the best of both worlds? That's where elastic net regression comes in. Elastic net combines both L1 and L2 penalties, allowing us to shrink some coefficients while completely eliminating others. It's particularly useful when we have a mix of correlated and irrelevant features, and we need a flexible way to handle both. At the end of the day, the choice between Lasso and Ridge depends on our specific dataset and goals. If we need a sparse model with only the most important variables, Lasso is our best bet. If we want to keep all predictors but reduce their impact, Ridge is the way to go. And if we're dealing with a complex dataset with both redundancy and noise, ElasticNet gives us a balance of both approaches. So now that we've compared Lasso and Ridge, let's take a look at how Lasso is actually used in the real world. Where do we see it making a difference? What industries rely on it the most? That's what we're diving into next. Real-world applications of Lasso regression. Stay with me. So, now that we understand how Lasso compares to Ridge regression, let's talk about something even more exciting, real-world applications. Where do we actually see lasso regression making a difference? Why do industries rely on it? And how is it helping professionals make better decisions every day? Lasso isn't just a theoretical tool, it's actively shaping fields like finance, healthcare, and marketing. Its ability to automatically select the most important predictors makes it incredibly useful when working with large, complex data sets. Let's explore some of its most impactful applications. One of the biggest areas where Lasso shines is finance. Banks and credit agencies deal with huge amounts of financial data, and they need models that can identify the most relevant risk factors while ignoring the noise. Take credit scoring, for example. A bank wants to predict whether a customer will default on a loan. They have dozens, maybe even hundreds of possible factors to consider: income, age, debt history, spending habits, loan amount, interest rate, and so on. But not all of these predictors matter equally. Instead of manually selecting which features to keep, Lasso automatically removes irrelevant variables and keeps only the ones that are truly useful for making predictions. The result? A more accurate and interpretable credit risk model. Now let's move to healthcare, where Lasso is making a huge impact in genomic research and medical diagnosis. Imagine you're trying to predict a patient's risk of developing a disease based on their genetic data. You're dealing with thousands of genetic markers, but only a handful are actually relevant. A traditional regression model would struggle. It would keep all variables, making it too complex to interpret. But Lasso, it filters out the noise and highlights only the most important genetic markers associated with the disease. This is game-changing for medical research because it helps doctors and scientists focus on the real risk factors, leading to better early detection and more effective treatments. Now let's switch gears and look at marketing. Businesses want to understand which customer behaviors drive sales. A company might have data on website visits, email clicks, social media engagement, past purchases, and more. With so many variables, it's hard to tell which ones truly influence customer decisions. Lasso helps cut through the clutter by keeping only the most impactful features. Maybe it finds that email engagement is a much stronger predictor of future purchases than social media likes. With this insight, the company can focus its efforts on what actually moves the needle and stop wasting time on factors that don't matter. And let's not forget sports analytics. Teams and coaches use Lasso to analyze player performance. Let's say an NBA team is trying to find out what makes a player valuable. They have data on points, rebounds, assists, shooting percentage, defensive stats, and more. Instead of considering every possible statistic, Lasso selects the ones that truly contribute to winning games. Maybe it finds that defensive efficiency and three-point shooting matter more than total points scored. That insight helps teams make better draft decisions, player trades, and in-game strategies. The common theme in all of these examples? Lasso regression simplifies complex datasets, focusing only on the features that truly matter. Whether it's predicting loan defaults, identifying disease risk factors, optimizing marketing strategies, or improving sports performance, Lasso helps professionals cut through the noise and make better decisions. Now, as great as Lasso is, we've seen that it has some limitations. It aggressively shrinks coefficients to zero, which is great for feature selection, but can introduce bias in some cases. It also doesn't handle situations well where many correlated variables each have partial importance. So before we wrap up, let's take a final look at what we need to keep in mind when using Lasso, along with a summary of everything we've learned. Let's bring it all together. Welcome to the last mile. So we've covered a lot, from how Lasso works, to its advantages, to its real-world applications. But before we wrap up, we need to take a critical look at its limitations, because while Lasso is a powerful tool, it's not perfect. Like any method, it has trade-offs, and understanding them helps us use it correctly. One of the biggest challenges with Lasso is that it can introduce bias into the model. Since Lasso forces some coefficients to exactly zero, it might remove variables that actually carry some predictive power. This is different from ridge regression, which shrinks all coefficients but never fully eliminates them. So, if you're working in a situation where every predictor contributes a little bit, Lasso might be too aggressive in its selection process. Another issue is how Lasso handles correlated variables. We saw earlier that when two predictors are highly correlated, Lasso picks one and drops the other. That's great for simplifying the model, but the problem is it doesn't always pick the right one. The variable that gets kept isn't necessarily the most meaningful, it's just the one that had a slightly stronger initial correlation with the outcome. This means we need to be careful when interpreting results. If important variables get dropped, we might need to adjust Lambda or reconsider the feature selection process. Lasso is also very sensitive to Lambda. If Lambda is too small, we don't get much regularization, and we're back to a model that overfits. If Lambda is too large, we lose too many features, and the model becomes too simple, leading to underfitting. This is why cross-validation is crucial when choosing the right Lambda value. We need to systematically test different values and find the one that provides the best balance. Another challenge? Lasso struggles when the number of predictors is greater than the number of observations. While it does perform automatic feature selection, it's not always the best tool for extreme high-dimensional cases like genetics research, where you might have thousands of predictors but only hundreds of observations. In those situations, hybrid methods like elastic net, which combines Lasso and Ridge, often work better. And finally, there's the interpretability factor. Yes, Lasso makes models simpler by removing unnecessary variables, but this comes at a cost. If you're working in a field where understanding the relationship between all predictors is important, like medicine, where small interactions between variables might be critical, then removing too many features can make the model less informative. So, does this mean we shouldn't use Lasso? Absolutely not. It just means we need to be aware of these limitations and use Lasso when it makes sense. If our goal is to create a lean, efficient model with only the strongest predictors, Lasso is fantastic. If we're dealing with a lot of correlated variables that all have some importance, we might consider Ridge or elastic net instead. Now, let's bring everything together. In our final slide, we'll summarize everything we've learned, why Lasso works, when to use it, and how it can transform the way we approach regression modeling. Let's wrap this up. All right, we've been on quite the journey, breaking down Lasso regression from the ground up. Now, let's bring everything together and summarize the key takeaways. Lasso regression is more than just a regression technique. It's a powerful tool for feature selection, model simplification, and preventing overfitting. Unlike traditional regression methods that keep every variable, Lasso actively shrinks coefficients and removes the ones that don't contribute much. This makes it incredibly useful for high-dimensional data sets, where we need to filter out noise and focus on what truly matters. At its core, Lasso works by adding a penalty term to the regression equation. This penalty forces some coefficients toward zero, meaning certain predictors get eliminated. The key factor controlling this process is Lambda. If Lambda is too low, the model keeps too many variables and risks overfitting. If Lambda is too high, we lose too much information, leading to underfitting. The trick is to find the perfect balance, usually through cross-validation. One of Lasso's biggest strengths is that it handles multicollinearity. When predictors are highly correlated, Lasso picks one and discards the rest. This makes the model more stable and easier to interpret, but at the same time, this is also one of its limitations, because Lasso doesn't always pick the best variable, just the one with a slightly stronger initial correlation. We've also seen how Lasso is used in the real world. From finance, where it selects the most important risk factors in credit scoring, to healthcare, where it helps identify key genetic markers for diseases, to marketing, where it pinpoints customer behaviors that drive sales. Lasso helps professionals make smarter, data-driven decisions. But like any tool, Lasso isn't perfect. It can introduce bias by eliminating too many predictors, and it might not work well when all variables carry some level of importance. In cases like these, Ridge Regression or Elastic Net might be a better choice. So, what's the final takeaway? Lasso is an incredibly useful method when we want a simple, interpretable, and efficient model. If we have too many predictors and we need to focus only on the most important ones, Lasso is our go-to. But we always need to tune Lambda carefully and be aware of its limitations when working with correlated variables. And that's it. We've gone from understanding the problems with ordinary regression to seeing why we need regularization to exploring how Lasso improves model performance and finally looking at its real-world applications and trade-offs. Now, the question is, how will you apply Lasso in your own projects? Whether you're working with business data, medical research, or predictive modeling, the ability to simplify and refine your models is a game changer. So, go ahead, experiment with Lasso, tweak Lambda, test different data sets, and see how this technique can transform your work. And if you found this useful, don't forget to share it, discuss it, and apply it. Thanks for joining me on this deep dive into Lasso regression. Until next time, keep exploring and keep learning.